All right, welcome to freeCodeCamp OKC. My name is Kimberly Collins. I'm one of the co-organizers of the group, and today I'm going to be talking about database design, giving you just a quick intro. And by the way, if you feel bad about your portfolio and want to see like an even worse example, check mine out. Maybe that'll embarrass me enough to get some work done on it. It's as much under construction as anybody's is, so there you go. Our group chats in Slack. If you're not familiar with that, check it out. You can go to this URL to join. We're in the freeCodeCamp channel, so that's where our group chats about anything even remotely related to freeCodeCamp. If you have questions for me, you can send them to me. Right now, I've got my Slack muted so that doesn't distract me. So if you do have questions and maybe you feel intimidated to raise your hand and ask, feel free, and I'm volunteering Carson and Daniel that if you have questions, send them to him if you would like them to, ask for you if you're not sure. Because last time there were some questions that I didn't get to. So if you don't understand something I'm saying, please ask me. If you want to go into more depth later, we can do that after the talk. But if you have questions and you don't understand what I'm saying, please stop me. We're here at Starspace 46, which is a great place to have events here in their event center. They also have a co-working area where I'm a member and I come and hang out and do work. They have a meetup group that I would recommend that you all join if you're interested in attending events here. Check them out on Twitter, Facebook, and Instagram to see what they're up to. Same with Techlahoma, that's our sponsor, and they sponsor lots of other groups around the state. You can find them on Meetup, and that's the best place to find groups sponsored by Techlahoma and just groups about anything you might be interested in. We stream on Twitch. You can find Techlahoma also on YouTube, Twitter, Facebook, Instagram, all these places to see what they're up to. A couple of meetups this week that I would recommend that you might be interested in. This week we've got several going on here. Tomorrow at lunch is the C# group and then the design group in the evening. Java, Python, Ruby, pretty much anything you even are remotely interested in, come get some free pizza. RSVP on meetups, let them know you're coming. But these are some groups that I really recommend checking out, especially the Hack Night on Tuesday at 6. We'll be in here just working on whatever you want to work on. Whether it's freeCodeCamp exercises or your portfolio or whatever, and just come and hang out. So the meetups that are coming up for our group specifically, next week, I would really recommend that y'all plan to come to the How to Get a Job panel. That one's not going to be streamed, so if you're interested at all, you'll have to come and join us in person to see that. And then the next week, we're going to have a talk on accessibility. Usually on the fourth Sunday of the month, the Nerdy Girls Code Club meets after our group, but on the 23rd, we're going to be combining and having a longer session, a special guest speaker coming to tell us about accessibility, which is a really important topic. And then the week after that, we'll have our monthly campfire talks, which is lightning talks. The people in the group give just about 5 or 15 minutes about some topic that you're interested in. So if you're interested in doing those in the future, let me know and we'll get you scheduled. But today we're talking about database design, which doesn't really fit under the JavaScript world that we've been dealing with lately, but I think it's really important for you all to know about, even if it's not something you'll ever work with, just to be aware that it exists and the fundamentals about it. Or maybe you'll learn a little bit about it and find that it's something you really love, and I really love it. I've been working with this for 11 years. SQL, and everything I say today, there'll be someone who argues about the semantics of the details. You can say SQL or SQL, regardless of which one you say, people say you're saying it wrong. It stands for Structured Query Language, and that's the language that we use to query the database. So I've been working with that for 11 years. The only course I have ever taken in databases was Oracle, literally 11 years ago, and I've never used it and forgotten everything about it. So everything has been on-the-job training, learn as you go. I don't have any sort of formal database training other than that. But I've been designing and developing and maintaining databases, hundreds or probably even thousands of tables throughout my career. This is something I really love to do and I'm interested in, and I hope that y'all, if this is maybe not something you want to do in the future or just kind of interested, that's why you're here, to learn a little bit about it. So the process that I use, we're talking that there might be other processes that other people use, but this is kind of how I define what I do. And I'll be going through what I mean by each of these 4 steps throughout the talk. The first one is determining what the entities of your system are. And then next, you'll determine the relationships between those entities. The third step is determining the attributes of each entity. And then the 4th step is when we actually get into the database. So the first 3 steps, we're not even in the database yet. The 4th step is when we start creating that database table structure. And the key idea of everything we're talking about here is normalization. This is a relational database, meaning that we have lots of different tables and columns that all relate to each other. So if you're coming from the JSON world, this might seem a little strange and hard to get used to, where in a JSON object you have pretty much everything you need about that thing right there. the children or whatever. This is totally different where we're breaking data apart as much as we possibly can. So we're optimizing for data storage efficiency, not necessarily for human readability. And I think that's one difference between relational databases and other systems is we're trying to think about the best way to store the data. And then if you go look at the data, it might not be completely readable to you. So some of the purposes of normalization, the first one is to improve integrity. And by that we just mean sort of like the trustworthiness of the data. We don't want to have orphaned records. We don't know who this order belongs to, or somehow records get deleted or moved around or changed. We want the data to be, we use the word integrity. We want integrity of the data. We want to reduce redundancy, which redundancy sounds like it might be a good thing. And definitely having backups of your entire database is a very good thing. But redundancy within your database is actually a bad thing. One example I've heard of this is that if you have one watch, you keep it up to date and you always know what time it is. The time on the watch, that's what time it is. If you have two watches, eventually they're going to get out of sync. Either one's running faster than the other, you change time zones, you update one, you forget to change the other. You never know what time it is when you have two watches. You always know what time it is when you have one watch. So that's an example of where having more data is actually bad, because eventually it's going to get out of sync and you don't know which one to trust. And we really want the data to be trustworthy. We want this integrity of the data. And also just to save space, that's not a huge consideration, but that is one reason to only store each thing in one place in your database. And we're avoiding anomalies, and the update anomaly is one where data gets updated in the wrong way, and now we don't know what to trust. So that's what we're trying to get at throughout this database design process. We want the data to be normalized, and it's for the purposes of integrity mainly. So the first thing you want to do when you're designing a database for a system is determine the entities. When you're talking to a user, and when I say user, I mean anyone on the business side, that might be a business analyst or an end user. Most of the systems I've worked with, I've been able to work directly with the end users and hear the words they use to describe the things in the system. So if a user says, well, students enroll in classes. Okay, well, those are two nouns right there, students and classes. I'm going to make a list of these words they're using that might be the things or the pieces of the system. Another example, in an ordering system, customers are creating orders that contain items. So those three nouns, customer, order, and items, most likely are going to be tables or entities in our system. And you notice that some of these are singular, some are plural. I don't really have a strong preference either way, as long as you keep it consistent. So if your database has singular words for table names, stick with that. If they're plural, that's fine too, but try not to mix them. So the next step after you have an idea, and this is iterative, you'll go through this process. As soon as you have an idea of some of the entities, you'll start thinking about how they relate to each other. And the main question you're going to ask yourself over and over is, can one instance of this one entity have or belong to multiple instances of another, and vice versa? This is the question we're always asking, is how do these relate to each other? Can I have just one of these? Can I have many of these? And I'll get into the details of those. But that's the main goal here, is determine what the entities are and how they relate to each other. So the types. One-to-one is a type that we don't use all that often. I'm not going to go over it. The two types that you're going to be using all the time are one-to-many and many-to-many. And when we say many, that could be any number from 2 to 2 million. We don't really care about how many there are. We use the word many to mean multiple or just more than one. So we care a lot about the difference between one and more than one, but past how many are there more than one, that doesn't really relate to what we're doing here. And so the goal, and I brought my marker board. This is my high-tech solution when I'm designing databases. I like to draw it out, and I'll show you an example of where I've done that. But our goal is to have a diagram that represents the entities and the relationships between the entities. So what you'll do is draw a box for each entity, put the name inside of it. Actually, my pro tip is to write the word first and then write the box around it, draw the box around it. Most people do it the other way around and then end up squishing their words together. Write the name and then put a box around it. And then any pair of entities that are related to each other, draw a line to connect them. And then we use what we call a crow's foot to indicate the many side, which I know at this point makes no sense, but hopefully it will soon. The first type of relationship I want to talk about is one-to-many. And that's generally noted by 1:M or 1:N. This is basically a parent-child relationship. One of the first entity can be associated with any number, many, of entity B, the second entity in the relationship. That could be 0, 1, or more than 1. But the reverse is not true. One of the second entity can only be associated with one of the first entity. and I hope this will make a lot more sense once I show you an example, which is customers and orders. One customer can have no orders, one order, many orders, but any one of those orders has to have exactly one customer. In our system, maybe in other systems, I don't know, in our system, I've talked to the user and they say, okay, yeah, an order can only belong to one customer. Two customers can't share one order. That wouldn't make sense. This is something you're wanting to find out from the business side. Can this ever happen? If it can happen anytime that one order can be shared by two customers, we need to know that because that'll turn it into a many-to-many relationship. So lots of times users will tell you sort of the general thing that's mostly true and kind of ignore the fact that that can be, that's not always true. So you'll need to find out, can this ever happen? Has this ever happened? Will this ever happen? And if they say no, one order must belong to exactly one customer, then we're going to continue with this being a one-to-many relationship. So this is how I draw on my marker board. This is literally what I did and what I do when I'm designing a database. I write the word customer, draw a box around it, write the word order, draw a box around it, connect them with one line, and then think about which side of this is one and which side of this is many. So one customer can have many orders. So we have one line pointing to customer here, but then we have what they call the crow's foot, the 3 lines representing that this one customer can have multiple orders. So this is the line that we'll see all the time in our entity relationship diagram. So as opposed to one-to-many, we have many-to-many. And that's usually denoted with the M:(N). And this way is like one-to-many, but it's true on both sides, in both directions. One of entity A can be associated with 0, 1, or more of entity B, and vice versa. One of entity B can be associated with any number of entity A. And again, I hope this makes more sense with an example. Please stop me if I'm saying something that doesn't make sense to y'all. The classic example of this is students and classes. One student can have any number of classes. I might not be taking any classes this semester. I might be taking exactly one or more than one, and we use the term many to mean that. Even if it's not a lot, if it's only 2, we still call that many. And the reverse is true. One class can have any number of students. 0 students in the class, 1 student in the class, or multiple in the class. So this is an example of a many-to-many relationship. It's one-to-many in both directions. Another example, orders and products. One order can contain multiple products, and one product can be ordered by multiple people or in multiple different orders. So this is an example of a many-to-many relationship. When we're diagramming this, we need to represent this many-to-many relationship as its own entity. So we have the 2 entities, for example, orders and products, and the relationship between the 2 has its own entity in the diagram. Sometimes that relationship will have a name, like students and classes. The relationship between those 2 has a name. We call that enrollment. But sometimes there's not really a good name for that, and so you'll just combine the names in a way that makes sense to you to describe that relationship. So my example here, I have my one customer with multiple orders, and I also have items that can be ordered. Well, one order can contain multiple items, and one item can be in multiple orders, so I have to have this order items, what I decided to call it, entity sort of between the 2 to join them together. So I have my one-to-many crow's foot on both sides, and I guess every time I put the cursor over, you can't quite see what I'm showing. But I can't have crow's foot on both sides. It has to be one or the other, but not both. So I have my order is one-to-many with order items, and item is also one-to-many with order items. But I can't go directly between order and item. I have to have this third entity that represents the relationship between the 2. So the first step was determining the entities. The second step was determining the relationships between the entities. The third step is going to be determining the attributes, which are the properties of an entity. So the entities are going to have tables, and the attributes are going to be columns in that table. This is where I go back to my marker board and start drawing out, maybe there's an order date. Which table should that go on? Maybe there's a count or a description or a name determining which entity has which properties. So once we've determined those things, we're going to start thinking about tables. So up until this point, when I'm generally doing this process, I like to use my marker board because these relationships, these entities exist outside of the computer. This is part of the business system. But step 4 is when I actually go back to my keyboard and start typing. So I like to, when I'm thinking about the relationships between the entities, do that on my marker board to kind of think a little more creatively, think a little outside the box, and think about, okay, what are the relationships here that exist outside of the computer system? But in step 4, now we're ready to start actually creating tables. And tables have rows of data and columns. In the database world, we don't really use the term cell as much as you would in a spreadsheet. But if you're familiar with Excel, you would think about the rows and the columns, and the intersection between the two are cells. But I do want to say that Excel is not a database. Spreadsheets are not databases. The way we use spreadsheets makes sense in that context. But when we start to design normalized tables for a relational database, we do things a little bit differently. The spreadsheet is generally intended for a user to be reading, where a database isn't necessarily. It's for the computer optimizing storage there. So in normalization, there are several different levels. The one that's the most important is obviously the first one. It's called first normal form. By the way, if you go to Wikipedia and look any of this up, you will definitely be intimidated by all the technical jargon they use. They get really into mathematical notation. Don't worry about too much of that. Don't feel intimidated if you go to research this and you see things that look intimidating. Find a website, if you're Googling this, that brings it down to a more practical level along these lines. So for a database to be in first normal form, we're going to have a table for each entity. Each row in the table needs to be unique. There's going to be a primary key identifying each row. The rows and the columns can be in any order, and that's a big difference between databases and spreadsheets. Is in the spreadsheet, you really want the columns to be in a certain order, and it might not even make sense if you switch the order to columns. And we can have our preference the way we would like to see the columns displayed, but if the table only works if the rows are in a certain order or if the columns are in a certain order, you're violating first normal form. They need to be a little bit more, I guess, independent. And then the big one, also a big difference between databases and spreadsheets, is that a cell can only contain one value. You can't have multiple values in the intersection between a row and a column. That's a cell, it can only have one. People argue whether null is a value. I don't want to get into null too much, but it's the absence of value. But what you can't have is two or more values within the same cell. And a great example of that you'll see all the time in a spreadsheet, you'll have a list of people, a column for first name, a column for second, a column for last name, and then a column for phone number. Well, as soon as you do that, of course, someone wants to give you two phone numbers. And that's perfectly fine to do in a spreadsheet or in a non-normalized database. But if our goal is normalization, we can't have that comma-separated list. That's violating first normal form. It's always better to store those values separately and then combine when you need to, instead of storing combined and separating when you need to. We want to store each thing separately. So in the case of people and phone numbers, we would probably have a person table and store the multiple phone numbers in a one-to-many table, because you can have multiple different phone numbers. The primary key. Each table needs to have a primary key. It's the unique identification for a row. Lots of times we'll use an auto-incrementing integer, and we call that identity, and we'll name the column ID. But it doesn't have to be that way. You can use a code, or you can also use the combination of multiple columns. And that is what we'll do in that many relationship table, is we will probably not have a primary key that's an identity for that table. Foreign keys are the relationships between the columns. So in that diagram that we drew out, we have lines between entities. Those are the foreign keys. Because each entity is going to have a table, and then the relationship between the tables, you can have a foreign key pointing back to that same table, but in general, a foreign key is relating two different tables to each other. So an example in our system is the order table is going to have a customer ID, and the customer table has an ID. And we'll have a foreign key pointing from the order customer ID to the customer's ID. So back in my drawing, the entities now are going to represent tables. I'm going to have a customer table, an order table, and the line that connects them on the diagram represents a foreign key. So there's a foreign key from the customer ID in the order table pointing to the ID in the customer table. And the reason we do that is to constrain the data. The value in the first column has to already exist in the second column, or SQL Server won't allow you to insert the new record. We can't have an order that belongs to customer 123 if there is no customer 123. We want integrity of our data, so that orphaned record, we don't want that to even exist in the database because it wouldn't make sense. Like we said, an order must have a customer it belongs to. So that's protecting against orphaned records. So joining tables, that's where I think it gets a little bit confusing if you're not used to these things. But the many-to-many relationships have to have a table between the two entity tables. So in the case of students and classes, we will have a table in between them called enrollment. Just like in our diagram, we had 2 boxes, one for students, one for classes, and we had to have a box in between them representing this relationship. That's going to be an actual table in the database. And that joining table will have a foreign key back to both of the 2 entity tables. So in our example of orders and items, order is a table, item is a table, and so is order item. We have this third, we call it a joining table or an intermediate table, a junction table. It has several different names. I use the term joining table. So order item is a joining table. Because again, we can't have this many-to-many relationship between order and item directly. We have to have something in between. So we'll have a one-to-many relationship from each of the 2 entities to the joining table, but no many-to-many relationship directly between the 2 entities. So when we're querying the data, I don't want to get too much into querying, but I do want to show you how this works to get the data back. If I have an enrollment table and I want to see the data, I'm going to do select star. Star means everything from the enrollment table. And this will probably have a student ID column and a class ID column, which are just going to be numbers. So that's not going to be really helpful to me as a user to see student number 1 is in class number 2. I want to see a list of people's names and the names of the classes. So the way I get that is joining the tables together. So I have the enrollment table joining to the student table. On is representing that foreign key relationship. The student ID in the enrollment table needs to be equal to the ID in the student table. And then same thing for class. The class ID in the enrollment table is going to be equal to the ID in the class table. And the last thing I do is the first line, selecting which columns do I want to see. So I've sort of defined this relationship in the main body of the query, and now I decide that I'd like to see the student's first name and the last name and the name of the class. So this is how we go from the data being stored separately, optimized for storage, into something that makes more sense for a user. And we were talking about tables, but there's something also called a view, and that's basically a saved query. And so I can send that to a report or to a screen for a user to see in a way that makes more sense for the user. And we call that flattening the data. So if you're interested in learning about databases, this kind of piqued your interest, the first thing I would recommend doing is finding the AdventureWorks sample database from Microsoft and kind of looking into the way the tables there are arranged, and how you'll see these one-to-many and many-to-many relationships. If you're wanting to talk about databases or just learn more or share links in the Techlahoma Slack, there's a databases channel, and that would be a good place to ask your questions or share like the video that was posted to learn a bit more if this is interesting to you. There are 2 local database meetups. One is OKC SQL, and they meet the 3rd Monday in the evening, so there'll be one next week. They're having lightning talks, and those are always a great one to go to if you can. And then the open source database meetup meets on a Thursday, I'm not sure which one, again in the evening. So if that's a convenient time for you to come here and learn more about databases, I would definitely recommend joining those 2 meetup groups. And that's essentially all I have on the slides. Did y'all have questions? Does the many-to-many relationship make sense?